Hello guys, welcome to our class for today. This is Noble My Science Tutors Online, and today in our physics class we are still discussing gas laws, and today we'll be looking at Sharp's laws, pressure law, and the general gas equation. Then we'll also discuss briefly work done by an expanding gas. Okay, so please get your writing materials ready so that we can go straight to our class. And please, if you have not subscribed to this channel, please subscribe to the channel, click on notification bell so that whenever we upload a new video, YouTube will notify you. So okay, you can also reach us via the WhatsApp number that is showing on your screen. Okay, so if you are ready for our class for today, we'll be starting with Sharp's law. Then we'll solve some problems before we'll now go to pressure law and general gas equation. Is that okay? So we've already started our class on. We've treated Boyle's law, we've treated pressure and measurement of pressure. So this class is a continuation of what we started discussing before, right? So you are welcome to this class for today. Let us go straight to our lecture room. Okay, so Sharp's law. From your secondary school, we've already know that Sharp's law has to do with volume and temperature changes. Okay, so Sharp's law says that the volume of a given mass of a gas is directly proportional to its absolute temperature, provided the pressure is constant. Okay, so mathematically stated, V is directly proportional to T, or the equation can be written like this when you take the constant of proportionality. So you can have this equation V over T, and for a gas that has an initial volume at a particular temperature, you can actually calculate the final volume at another temperature. So that is why you have this equation V1 over T1 equals to V2 over T2, where V1 and T1 are the initial volumes and initial volume and temperature, and then V2 T2 is equals to the final volume and final temperature. I want you to take note of the fact that when you are working with temperature, in this instance you have to convert it to the Kelvin temperature. Okay, so whatever temperature that is given to you in centigrade, you have to convert it to Kelvin temperature by adding it to 273 Kelvin, right? Okay, so that's what you have to do. So basically, this is the pressure law, and these are the equations for the pressure law. And without wasting time, we just have to see how we can use this equation to solve some problems. Is that okay? So that is exactly what we want us to do now. So we'll be solving some problems on this particular equation that we just discussed, right? So let's go. Okay, so this is sample question 1. Say that the volume of a fixed mass of gas is 40 centimeter cube at 27 degrees centigrade. What is its volume at 90 degrees centigrade if its pressure remains constant? Okay, so for this particular question, you will be given an initial volume to be equals to 40 centimeter cube, right? Then initial temperature T1 is given to you to be 27 degrees centigrade. So this, I said, you have to convert to degree Kelvin, so which means you are going to add this to 273. So to convert it to Kelvin temperature, okay, so you have to do that. So this will be in Kelvin, and this will give you what? When you do this addition, you have 300 Kelvin. Okay, so that is 300 Kelvin. Alright, so that is what you have. Then we are given you are asked to find V2. So V2 you don't know, V2 is unknown, and T2 is given to you too. So similarly, just like you did for this other one, you do the same. You convert 90 degrees centigrade to degree Celsius, to degree Kelvin, into Kelvin. So you add 90 degrees Celsius to 273 will give you your answer in Kelvin. So when you do the addition, you're going to have 363 Kelvin. Okay, so this is your T1 and this is your T2 and this is your V1 and your V2 is what you are looking for. So writing that equation down, you have V1 over T1 is equals to V2 over T2. So T2 is what you are looking for. So we make V2 that you are looking for, or the unknown, your subject of formula. So your equation becomes V1 times T2 all over T1. So what you now do, just substitute the values that you have gotten up there, these values you have here, your T1, T2 and your V1, substitute them into this particular equation. So when you do that, you are going to have V1 is your V1 T2 over this. So you are going to have that your V1 is equals to 40. Your 40 multiplied by T2, which is 363 divided by T1, which is 300. Okay, so you can punch this out with your calculator. So when you do that, when you do this multiplication, 40 times will give you 14,520 divided by 300. Okay, so by the time you do that division out, you are going to have that V2 will be equals to 48.4. That's 48.4 centimeter cube. Alright, so this is how to apply the Charles law to solve problems. Well, okay, so that is question number 1. We'll also try another question now. So I hope this one is okay and simple to understand. Alright, so this is another question. Okay, so this one says that dry oxygen is trapped by a pellet of mercury. Pellet of mercury in a uniform capillary tube which is sealed at one end. The length of the column of oxygen at 27 degrees centigrade is 50 centimeter. If the pressure of the oxygen is constant, at what temperature will the length be 60 centimeters? Okay, so this also is another question that we're going to look into. Now here, the length of the trapped gas is equals to its volume. Is that okay? So, and that is exactly what we're going to use to solve this problem. Okay, so here you are given that your V1 is equals to 50 centimeters. Okay, please pardon my writing. And then your T1 is equals to 27 plus 273. Already, I hope you know why. So we are converting it to Kelvin already. So that gives us 300 Kelvin. Alright. So that's your T1. Your V2 is given to you to be 60 centimeters. And what you are looking for is your T2. T2 is your unknown. So basically just use that equation, V1 over T1 is equals to V2 all over T2. Okay, so you are looking for T2, so you make T2 your subject of formula. Okay, make T2 your subject of formula by cross multiplying. So you have that T2 is equals to V2 times T1 all over V1. So when you substitute into this formula, substitute your values that you have here into this formula. So that will give you V2 is 60, T1 is 300, and your V1 is 50. Okay, so you can work this out. You work this out, you were going to have, by the time you solve this out, you'll have your answer in Kelvin, and that will give you 360 Kelvin. So your T2 here is equals to 360 Kelvin. See, so application of the pressure law is very simple and it's easy. Just get the basic understanding, and then there's no problem you will not be able to solve on this. Okay, so this is the pressure law, and then the application of, this is the Charles law and the application of the Charles law. So right here we'll go into the pressure law. Pressure law is also related to Charles law in some ways, just some change of variables. Okay, so this is pressure law. The pressure law states that the pressure of a fixed mass of gas at constant volume is directly proportional to its absolute temperature. So if you look at this, you see that the pressure law and the Charles law, they are basically related, right? So pressure directly proportional to temperature at constant volume, and this can also be written the way we wrote for the Charles law. And then when you have a situation, we have a system that has an initial pressure and a final pressure, an initial temperature and a final temperature, you can now relate the equations like this: P1 over T1 is equals to P2 all over T2, where P1 and T1 are initial gas pressure and temperature, and P2, T2, they are final gas temperature and pressure. Is that okay? So basically, just like we did for Charles law, that's what we're also going to do for this pressure law. So right away, we're going to solve some problems on this so that we can also get the understanding on how to apply this law to solve some problems, or these equations to solve some problems, right? So let's go straight to some questions. Okay, so this is a sample question. Okay, the question says that before starting a journey, the tire pressure of a car was 3 times 10 to the power 5 Newton per meter square at 27 degrees centigrade. At the end of the journey, the pressure rose to 4 times 10 to the power 5 Newton per meter square. Okay, so calculate the temperature of the tire after the journey, assuming the volume is constant. Calculate the temperature of the tire after the journey, assuming the volume is constant. Okay, so from the pressure law, we know that pressure is directly proportional to temperature at constant volume. So when you have when there's an increase in pressure, it means that there will also be an increase in the temperature. Is that okay? Or when there's an increase in temperature, it means that there will also be an increase in pressure, right? So we have been given initial pressure of the car to be P1 is given to us to be 3 times 10 raised to power 5. It's about 5 Newton per meter squared, right? Then we're also given that T1 is equals to 27 degrees Celsius. So basically, as we did for the other one, just convert it to temperature in Kelvin. That's okay. So if you do that, you are going to have that your initial temperature T1 is equals to 300 Kelvin. Okay, I hope that is clear. Then the final pressure is given to you to P2 is given to you to be 4 times 10 raised to power 5 Newton per meter squared. Okay, so I haven't gotten down this, and then T2 is the unknown. We don't know the final temperature. So I haven't gotten this. We can now bring in our equation that P1 all over T1 is equal to P2 all over T2. So what we are looking for now is T2. We are looking for final temperature. So you make the final temperature the subject of the formula. Okay, so your T2 will be equals to P2 times T1 all over P1. So substitute into this equation the variable or the value that you have gotten. When you substitute them, you are going to have that P2, which is 4 times 10 raised to power 5 times T1, which is 300, divide all by P1, which is 3 times 10 raised to power 5. Okay, so if you work this out, basically this can cancel this, and this we have 1 here, so this will be 100. So when you work that out, you're going to have that your T2 is equals to 400 Kelvin. So from our calculation, we have gotten that T2 is equals to what? 400 Kelvin. Okay, so I hope this is simple and it's easy to understand, right? I hope this is simple and easy for you to understand. So if you have any question that has to do with pressure law, this is the equation, and then this is how to go about it, right? So right away we're going to look at the general gas equation. The general gas equation. The general gas equation is a combination of all the laws that we have discussed. We've discussed Charles' law. We've also discussed Boyle's law. So the general gas equation, we discussed Charles' law, we discussed Boyle's law, we also discussed pressure law. So the general gas equation is a combination of all the laws. It is a combination of all the laws. Okay, so it's mathematically stated. This is the equation. That is the general gas equation. Okay, so for a gas that expands from particular volume at a particular pressure and temperature to another volume at another temperature and pressure, you can now write this equation at P1 V1 all over T1 is equals to P2 V2 all over T2, where P1 V1 and T1 they are the initial gas pressure, initial gas volume, and temperature, while P2 V2 T2 they are the final gas pressure, the final gas volume, and the final gas temperature, okay, as the case may be. So basically this is the general gas equation, and you need to take note of this. And then so we want to see how you apply this general gas equation to solve some problems on gas laws, right? Okay, so this is a sample question that I want us to go to see. It says that the volume and pressure of a given mass of gas at 27 degrees centigrade are 76 centimeter cube and 80 centimeter of mercury respectively. Okay, so calculate its volume at s.t.p. s.t.p means standard temperature and pressure. That is the meaning of s.t.p, standard temperature and pressure. So this is your initial temperature, this initial volume, and then this is your initial pressure. Okay, so in this particular equation, you will be given T1 to be equals to 227 So just do that conversion the way we'll be doing before, so that can save some time. Okay, so convert this to your Kelvin, and then this will now give you 300 Kelvin. Okay, so this is your T1, 300 Kelvin. P1 is given to you to be 80 centimeter of mercury, and then V1 is given to you to be equals to 76 centimeter cube. Okay, then at s.t.p, standard temperature and pressure is equal to 76 centimeter mercury, and standard temperature is 273 Kelvin. So yeah, the volume is what we are looking for. So T2 at s.t.p, standard temperature is equal to 273 Kelvin. Okay, then standard pressure P2 is equals to 76 centimeter of mercury. V2 is what we do not know. So applying that equation now, we have that P1 V1 all over T1 equals to P2 V2 everything over T2. Okay, so once you have written an equation like this, your unknown, you make your unknown the subject of the formula. So by the time you cross multiply, we are looking for V2. Okay, so if you cross multiply this, you are going to have P1 V1 T2 is equals to P2 V2 T1. Now make V2 the subject of this formula, right? Make V2 the subject of this formula. So V2 will be equals to P1 V1 T2 all over P2 T1. Okay, so having gotten this, what you need to do next is just to substitute the values that you have already. Substitute all these values into this particular equation. So you have your P1 is equals to what? 80 centimeter of mercury multiplied by V1, which is 76 centimeter cube, multiplied by T2, which is 273 Kelvin. Then you divide by P2, which is 76 centimeter of mercury, multiplied by T1, which is 300 Kelvin, as we got above. Okay, so next you can now punch your calculator. This will cancel out. So punch your calculator. By the time you punch your calculator, you will have the final volume to be equal to 72.8 centimeter cube. 72.8 centimeter cube. Okay, so V2 in this particular instance is equals to 72.8 centimeters cube. Okay, so basically this is how to apply the general equation to solve problems on gas laws. The important thing is for you to be able to bring out all the variables, then do the equation. Any of the variables that you are looking for, just make that variable the subject of the formula. Then from there you can just solve, applying your basic mathematical knowledge. So please, you can still go and hone your skills on mathematics. That's okay, so that all these simple questions will not be difficult for you to solve and understand. Right, so thanks. So we are now going to look at very briefly, work done by an expanding gas. When a gas expands, work is done, and from your normal understanding of work is equals to force times distance, right? And distance can actually be in length, right? Your distance is also the same thing as length because you are measuring the space between two areas. So it can also be length, it can also be distance, as the case may be, and the two, they have the same unit too, right? So, and we know from pressure, we know that when we discuss pressure, we said that pressure is equals to force over area, right? That was what we talked about. So which means that from this definition, we can have that force is actually equals to pressure times area. Okay, force is equals to pressure times area. I hope this one is understood. So if you understand this, if you understand that pressure is equals to force times area, then we can actually put this equation into this equation of work done here, so that work done W becomes what? Force is pressure times area, as we have said, times distance, which is L. So you can see that we are substituting pressure times area into the position of force here in that particular equation. Okay, so what we want to consider now is this area and length. Area and length is what we want to look at. So from here we say that work done is equals to P A L. So as I said, we want to consider this. Now we know that volume is equals to area times length, right? Volume is area times length, because you see this is meter squared times meters, so that gives you meters cube. I hope you can relate with that. Okay, so if you know that volume is equals to area times length, then we can equally substitute into this equation to give us our work done is equals to pressure times volume. Pressure times volume. Now, like what I said initially, work is actually done when a gas expands from a particular volume to another volume. So if that be the case, it means that work done would now be equals to pressure times change in volume. Is that okay? So this is what you have, and change in volume is equals to change in volume is equals to V2 is equals to final volume minus initial volume. This is change in volume. Final volume minus initial volume. Okay, so this is basically it, that work done. So work done by an expanding gas equals to pressure times final volume minus initial volume, which is equals to change in volume. So please take note of this equation, as we are going to use it now to solve some problems. Is that okay? So please, if you are preparing for JAM and all those these examinations, please take note of these simple equations, and then so that you know how to apply them. Right, so we are going straight now to solve some problems that we bring out how you can use this equation to maneuver through. Okay, so this equation, the volume of a fixed mass of gas increased from 0.04 meter cube to 0.32 meter cube, while the pressure remains constant at 1.5 times 10 to the power 5 Newton per meter square. How much work was done by the gas? Okay, so we know that work done is equals to what? Pressure times change in volume. Is that not? Times change in volume. Then here you will be given the two volumes. So here you have that V1 is equals to 0.04, and then V2 is equals to 0.32 meter cube. Take note of that unit, meter cube, and this also meter cube. Okay, so you change your volume is V2 minus V1. Okay, so it's V2 minus V1, and that is equals to 0.32 minus 0.04. Okay, so by the time you work that out, you will have 0.28 meters cube as your change in volume. So just substitute in this equation to give work done by the gas is equal to pressure. Pressure is given to you to be 1.5 times 10 raised to the power 5 multiplied by 0.28. Okay, so you can work that out. So when you work that out, you are going to have 4,200 joules. 4,200 joules of work done. Okay, so this is how to apply the equation for the work done by an expanding gas. So I hope this is basically easy for you to understand and comprehend. All right, so thank you so much. I think we're going to stop this class here, but before then, let's go to our test page. Okay, so this is our test page, and as I've always said, please try your hands on all these questions. They are meant to test your understanding and comprehension, so please don't avoid them and don't skip them. First question is the volume of an ideal gas at a pressure of 77 centimeter mercury and temperature 60 degrees centigrade is 240 centimeter cube. If the temperature and pressure are increased to 98 degrees centigrade and 81 centimeter mercury respectively, calculate the new volume of the gas. Okay, so this should be simple for you using the ID gas equation. And this one says a gas with an initial volume of this allowed to expand to 6 times its initial volume and constant pressure of this. What is the work done by the gas? Simple. This is what we just did now, right? And this one, a seed flask contains 600 centimeter cube of air at 27 degrees centigrade and is heated to 35 degrees centigrade at constant pressure. The new volume is, so this one has to do with Sharp's law, right? So volume over temperature has to do with Sharp's law. So you should be able to solve all this problem with ease, right? So thank you so much. But before I go, please, I'll still solicit that you subscribe to our channel and then click on the notification bell so that when we upload a new video, YouTube will notify you. You can also tell your friends to come and enjoy this physics lecture that is online. That okay? So this is Number Man Science Tutors Online, and you can reach us through the WhatsApp number. Please give us a like, give us a positive comment as we continue to work on this particular channel. Is that okay? So please, we want you to continue to study your books and then be serious. We want you to be better in physics. Yes, we want it better of you. So please continue to read your books, right? So thank you. We hope to see you in our next class. Thanks.